Mario Livio por estar disponible para dar esta conferencia plenaria de los cursos de verano de la Universidad Complutense en el Escorial. Y le voy a hacer la palabra al rector de la universidad.
Muy bien, muchas gracias, José Chu. Muy buenos días a todos y a todas. Y comienzo pidiendo disculpas por los minutos de retraso debido a los problemas técnicos que, bueno, parece que estamos resolviendo satisfactoriamente. Dear Professor Livio, es un placer tener al profesor Mario Livio aquí dentro de lo que el curso de las matemáticas a la sociedad, el camino de la divulgación. Como ustedes saben, bueno, o algunos saben, yo digamos, soy rector circunstancialmente, pero soy matemático, soy profesor en la Facultad de Matemáticas, con lo cual pues tengo una querencia natural hacia los cursos de verano dedicados a las matemáticas y en particular a este. Y por eso para mí es un placer el acompañarles y el estar aquí presentando al profesor Mario Livio. Es un gran científico, por una parte él es astrofísico, con más de 400 publicaciones en revistas de alto nivel, por lo tanto es un científico absolutamente reconocido, con premios, no me voy a extender en todo ello, miembro de la Asociación Americana para el Avance de la Ciencia y también es un gran divulgador de la ciencia. Y ahí es donde quiero poner el énfasis por el, digamos, subtítulo que lleva el título del curso, el camino de la divulgación. Afortunadamente vamos avanzando en la divulgación científica en nuestro país, pero nos queda todavía un largo trecho por recorrer. Y la divulgación científica es sin duda una obligación por parte de los científicos y además creo que es algo absolutamente necesario si queremos que la ciencia tenga el reconocimiento, tenga el apoyo social y tenga también el apoyo político que me parece que es inevitable si nuestro país realmente quiere salir adelante como un país moderno, basado en la tecnología, basado en el conocimiento, que es realmente el futuro. Así que estoy realmente encantado de poder presentar al profesor Mario Livio, de dejarle con todos ustedes. Hay libros suyos, creo, por ahí fuera, y creo que tendrá, si alguno quiere, puede tener la oportunidad luego de llevarse un libro firmado por el propio profesor Livio. Así que sin más preámbulos, les dejo con el profesor Mario Livio. Vamos a escucharle, vamos a aprender de él y de su múltiple experiencia ya como divulgador, como gran orador. Nos ha pedido, por supuesto, nosotros nos bajaremos y nos ha pedido que quitemos las sillas de detrás y esperemos que el micrófono inalámbrico le funcione bien. Dear Professor Livio, thanks for being here. It's a pleasure. And I just said that we have to work.
I understood most of it. I understood most of it.
Okay. Muchísimas gracias. Por favor, cuando quiera. ¿Las quitamos? Okay. It's okay.
It's okay? I think so. Yeah. Tell me when. It's okay? Thank you very much, Mr. Rector. Thank you very much, Jose, Roberto, for having me here. It's a pleasure. I also had the opportunity, even though I've been to El Escorial maybe 30 years ago, I really didn't remember all the splendor of the monastery here, which I visited yesterday twice. And it truly is a treasure, I can say. So it's a wonderful place to hold this. Now, I apologize that I have to speak in English because while I understand a little bit of Spanish, I cannot speak it. I can tell you, though, that the name of this book in Spanish is Errores Geniales. While I was writing this book, many people kept asking me, what is the book you're writing about? And I used to say, it's about mistakes, and it is not an autobiography. So why did I decide to write a book about mistakes? So there are two main reasons. One is a very simple reason, and the other is more important, and I will come back to it towards the end of the lecture. The very simple reason is that it is comforting to the rest of us to know that even some of the greatest geniuses made some serious mistakes. Now, how did I choose these geniuses? So, first of all, I decided to concentrate on 5 people. And I also decided not to go too far back in time. Because you see, if you go very far back, for example, let's say to Aristotle. Aristotle, essentially, everything that he said in physics is wrong. So, this does not make him any less of a genius than what he was. He just worked at a completely different time. So I only decided to go back to the middle of the 19th century. The second guiding principle that I used to choose my 5 people was that they are all connected by the concept of evolution. Evolution of life on Earth, evolution of the Earth itself, evolution of stars, and evolution of the universe as a whole. Now, in this talk today, I will not talk about 5 because there isn't enough time. I will just concentrate on 3 of them. So let me start. The first thing you notice about life on Earth is how diverse it is. It's enough to go outside here now, and you will see lots of plants, many birds, insects, people walking their dogs, and so on. Nobody actually even knows precisely how many species there are on Earth. The latest attempt to put a significant number on this puts it at 8.7 million species. But there are large uncertainties, and the number could be anywhere between 5 million and 100 million. And there are reasons why it's so uncertain. I mean, first of all, they discover thousands of new species every year. Second, you know, it's enough to take a teaspoon of dirt from under my feet, and that contains thousands of species in there. So there are lots of species. The second thing that is pretty amazing about life on Earth is a huge degree of adaptation. And this type of relation, which is, you know, scratch my back and I'll scratch yours type thing, which we call symbiosis. For example, you know, the bee is precisely the size that it fits into the flowers on which it feeds. And then, you know, it gets the pollen over its body and it transports it to another flower and so on. And this clownfish lives among the poisonous tentacles of the sea anemone. The fish protects the anemone protects the fish. The fish has this special mucus on its body that protects it against the poison of its host, and so on. Now, these 2 facts, a huge diversity and a very high degree of adaptation, convinced naturalists for many centuries that there must be some guiding hand and I don't know what and things like that. All of that changed in one blow with this gentleman, Charles Darwin, who in 1859 published this book on the origin of species by means of natural selection. Now, just as an aside, let me note that I like to, when I write books, I like to go to the places where things happened. So in this case, I also went and actually held in my hand the very first copy of Darwin's On the Origin of Species. And it's a very special feeling. Of course, you can see it on your computer screen, but it's still a different feeling when you hold in your hand the very first copy of this. I put this figure here not because it's correct, It's supposed to represent evolution, but it's just because it's very pretty from a graphics design perspective. The reason I say it's incorrect is that it gives you the impression as if things here are more evolved than things here. But that's not how evolution works. Evolution is not a ladder. It's more like a bush with things evolving in different directions. But things that are at the same distance from the origin, they are equally evolved. But it's still nice graphics design. So what is this theory of evolution by means of natural selection that Darwin introduced? First, I want to just make a small note. Darwin didn't like to publish these genealogy trees. He never published one. But in his notebooks, which I have seen, he sometimes drew them. But never published. And I like this one because you see it has primates, which are, apes here, and it has man over there. So he liked to do this to guide his thoughts, but he never published this. So what is this theory of evolution by means of natural selection? It is based on 4 pillars, which are all supported by one grand mechanism. And I will explain each one of those pillars. This figure, by the way, has nothing to do with Darwin's theory of evolution. It comes from a Hindu myth. But you see, it has 4 pillars which are supported by one grand mechanism, so I thought that it's appropriate. There is, by the way, a story which is almost certainly not true, but it is still a very good story. There is a proverb in Italian which says, "Si non è vero è ben trovato," which means even if it's not true, it's still a good story. So I'll tell you the story. The story is about mathematician and philosopher Bertrand Russell, who once gave a talk, and he had this kind of drawing. And then some lady from the audience asked him, "But on what does that giant turtle stand?" And he said, "On another giant turtle." And she said, "And on what does that turtle stand?" And he said, "Yet another giant turtle." And she insisted, "And on what does that turtle stand?" He said, "Lady, I'm afraid it's from there on, it's turtles all the way down." It probably never happened, but it's still a good story. Anyhow, what are these 4 pillars? So first there is the concept of evolution itself. Darwin tells us the species we see today did not always exist. Species are not immutable. The species we see today are those who evolved from other species that existed. In fact, 90% or more of the species that ever existed have become extinct. We only see today those that evolved from them. So that's the first concept. The second concept is the concept of gradualism, that things happen slowly. Darwin borrowed this from his geologist friends. In particular, Charles Lyell was the biggest geologist of the time, and he was a personal friend of Darwin. So what basically gradualism says in geology is that the surface of the Earth is very slowly shaped by the wind and the rain and the sun and so on. So Darwin said, yeah, this is how evolution happens. It's not that you will sit there and you will see one species turning into another. It happens over tens and hundreds of thousands of generations. The third is common descent. This is a powerful concept. Darwin tells us all the species we see today on Earth, they all started from one. Now, this concept is what is at the origin of, there are experiments today. I have a friend, Jack Shostak, who works at Harvard. He tries to develop life in the lab, from chemistry to turn into biology. Yes? Now, in order for you to do that, you must think that, all life had one origin, that, it's not just random things happen. And finally, there is speciation, which says, well, if it all started from one, how come that there are so many today? So Darwin tells us, well, look, what happened is that one species split, branched into two others, and then this one split into two others, and then this one split into two others. And since at every such node you double the number of species, very quickly you will get to huge numbers. And he drew this, again, in his notebooks, you know, like this, that you will have this speciation. I like this page a lot from Darwin's notes. Look, you probably cannot see it from the back. He says here at the top, I think. So he was very humble at that stage of life. He wasn't sure that that's how it is, but that's how he thought it was. Now, all of this, I say, is supported by one grand mechanism, and that's natural selection. Natural selection is one of those ideas that once you are told the idea, you say, oh, that's so simple. But, you know, all great ideas, once they are explained to you, they seem simple. So how does that work? Darwin tells us, look, suppose you have a certain species, and suppose some members of that species have something that gives them an advantage. An advantage both in terms of survival against the environment and all this and so on, and an advantage in terms of producing offspring, children, okay? If that's the case, then, Darwin says, over many, many generations, the whole population will shift toward that characteristic. Is that clear? You see, if you have a characteristic that gives you an advantage, and you produce more offspring, then over many, many generations, everybody will have that characteristic. That's the idea. Let's see some examples of this. So, for example, in England of the 19th century, there was this light-colored peppered moth, you see? And originally, it was so well camouflaged that, look, you probably did not even see it, that it is standing here. But then, you remember in 1848, there was the Industrial Revolution. They poured enormous amounts of soot into the atmosphere, which blackened all the trees. And then this light-colored peppered moth, you see, it sticks out like a sore thumb. It became the target of massive predation, and it almost became completely extinct. At the same time, the melanic version, the dark version of this moth, started actually thriving. So, luckily for the light-colored peppered moth, at some point even in 19th century England, they started to use a little bit greener practices, and that it was saved from complete extinction. This picture here just shows a few rat snakes that in different environments, you know, by natural selection, evolved with the right colors and so on. Now, look, from what I've told you so far, you see that Darwin came up with a theory that explains essentially everything about life on Earth. So where is the blunder? Where is the mistake? Well, the mistake had to do with heredity. Darwin didn't know any genetics because nobody knew genetics at the time. Even the word did not exist. Okay? So he adopted the theory of heredity that was the prevailing theory. That's not a mistake. He couldn't do any better. He adopted the theory that was there. What was the theory? The theory was that the properties of the mother and the father get mixed in the offspring just like you would mix paints. This is why I put some paints here. Okay? Just like you would mix paints. That was the theory. Like I said, this was not a mistake. The mistake was something else. The mistake was that Darwin at first did not understand that if this were the correct theory of heredity, natural selection could never have worked at all. And this was pointed out by an engineer named Fleming Jenkins. Now, why was there a mistake? And what did Fleming Jenkins realize? Look, Imagine that you have a population of 1 billion butterflies, and they're all white. And there is one butterfly that's black. And imagine that the color black is the characteristic that gives you an advantage in terms of coping with the environment and producing offspring. According to Darwin's theory, that means that over many, many generations, the whole butterfly population will turn black. Okay? Now let's see what would happen with blending heredity. The black butterfly will mate with a white butterfly. It will produce a gray butterfly, because you mix them like paint. Okay? Black will never appear again in this scheme. The gray butterfly will mate with another white butterfly, and it will produce a paler shade of gray butterfly. And that will mate with another white butterfly, and it will produce yet a paler shade of gray. Very quickly, you will have more than 50 shades of gray. Okay. I didn't know if this will work in Spain. But the population is not going to turn black. In fact, black disappears after one generation. So clearly, Darwin missed the point here that if blending heredity were correct, then it could not have worked. Now let me explain this a little bit in more detail now. So what happens in blending heredity? Suppose you have a property which I called capital A, which gives the color black. And I have a property which I called lowercase a, which gives the color white. From one parent you get this, from the other parent that, you produce gray. That's fine. However, in blending heredity, the capital A and the lowercase a cease to exist. They fuse together to form something new, because you mix them like paints. And that's it. You will never see black again. Now, what happens in Mendelian heredity, which is after Gregor Mendel, who did these experiments with peas, yellow, green, and so on. What happens is, you get one black and white, and you still get a gray thing here. But the capital A and the lowercase a continue to exist separately. And then from one parent you get this and that, from the other parent this and that. And depending on how you mix them, you will get black, gray, or white. And if black is the thing that gives you the advantage, eventually it will all turn black. Okay? Now, even though Darwin at first did not understand this, he was always unhappy about blending heredity. He felt that there was something not so good with it. And he wrote about this. In 1857, which was 2 years before the publication of On the Origin of Species, he already wrote that he thought that the theory of heredity will turn out to be something more like mixing of cards, not like paints. You see, the way heredity really works, according to Mendel, is more like shuffling cards, a deck of cards. If you have an ace, and having an ace is good, it doesn't matter how much you shuffle, you still have the ace. That's it, right? And then in 1866, Darwin wrote to Wallace something that you read today and you think, how didn't everybody think about it then? Darwin wrote to Wallace and said, wait a second, how is this that blending works? Because every female of the world produces a child that is a distinct male or a distinct female, and not some intermediate hermaphrodite. So he understood that there was a problem, only he didn't know how to correct it. Now, there are a few books that will tell you that when Darwin wrote that in 1866, it was not that he himself thought about this, but that he read Mendel's paper, which was published in 1865, about his experiments with peas. Now, this was not particularly important for the book, but I still decided to investigate this. And luckily, a person named Andrew Slater from the Darwin Project investigated this even before me, so I could rely on his findings as well. And what did we discover? Every piece of paper that Darwin ever had exists now. It's in the collection. Darwin did not have a copy of Mendel's paper. We know that. This is not surprising because Mendel's paper was published in the Annals of the Academy of Brunn, and Darwin was not subscribed to that, and so we didn't have that. These books, however, will tell you that he had two books which mentioned Mendel's experiments. And that turns out to be true. Now, in one of the books, the description of the experiment is so brief that you cannot tell from that even what the results were. The second book is this book, which I asked to be brought to me. It's by one Wilhelm Olbers Fouquet. And in it, there is, you see, this belonged to Charles Darwin. And in it, he describes a little bit Mendel's experiments. Now, do you know where he describes the experiment we discovered? It's in this page here, where the pages were never cut at the top. In old books, you had to cut the top. Darwin never read this book. He had this book, but he never read it. And in fact, I now read it. Had even Darwin read it, he would not have been much illuminated, because Fouquet did not understand the meaning of Mendel's experiment, so neither could Darwin. So Darwin did know about Mendel. Mendel, by the way, did know about Darwin. He actually had a copy in German on the origin of species, and he annotated it, and he underlined some lines, and so on. My second person is Linus Pauling. Linus Pauling was the greatest chemist of his time. Some might say the greatest chemist ever. He is the only person to have won the Nobel Prize twice by himself without sharing it with anybody else. There are others who won 2 Nobel Prizes. Madame Curie won 2 Nobel Prizes, but one in physics, one in chemistry, and she shared it. Linus Pauling won 1 in chemistry, 1 in peace, by himself. Here is Pauling kind of in midlife, pointing to his model for certain proteins. And here is Pauling when he was old, but the model stays the same, because the model was correct. What was this model? So Pauling had a very interesting way of working out models for proteins or other chemical substances. You see, at that time, people already knew how to do X-ray diffraction experiments. In X-ray diffraction experiments, what you do is you take the molecule that you want to study, you shine X-rays on it, and from the way the X-rays are scattered, you determine the structure of the molecule. Now, Pauling worked the other way around. He started from structural chemistry. He basically said, okay, what are the lengths of these bonds? What are the angles of the bonds? And from all of that, he constructed a model. And then he tested the model by X-ray diffraction. So he started from the other end and used X-ray diffraction only to test the model. So here in 1948, he was in England on sabbatical, and he tried to determine the structure of this protein. And he managed to convince himself that the carbon, nitrogen, and the 4 atoms that connect to them have to be in one plane. And then he started folding the paper in various ways to try to find the structure, and eventually he came up with this structure, which he called the alpha helix. not to be confused with the double helix of the DNA. This was the alpha helix model for proteins. And he was very happy with this, except there was one thing. In his model, the distance between two turns was 5.4 angstrom. 1 angstrom is 100 millionths of a centimeter. So the distance between his model was 5.4 angstrom. Yet in the X-ray diffraction, there was some feature at 5.1 angstrom. So you may think 5.4 angstrom, 5.1 angstrom, good enough for government work. But he was unhappy. He was so unhappy that he didn't publish his model for 13 years. 13 years. And during those 13 years, he asked his assistant, Robert Corey, to do X-ray diffractions on parts of the molecule. He asked Branson and others to try to see if there are other mathematical solutions to the structure and so on. After 13 years, he convinced himself that it must be okay. He published it. It turned out to be okay. This difference turned out to be from something that there was a helix within a helix, and that produced an artifact at 5.1. So he was very happy. Then he turned his attention to DNA. In 1948, he made a statement that I wish he had remembered some years later. And the statement was the following. Look, it's very, very clever. He said, if DNA is the thing that is supposed to replicate itself, it is easiest to replicate if your thing is composed of two parts that exactly complement each other. Because if that's the case, then if you know half the molecule, you already have the other half, because it's exactly the complement. Okay? So he had this insight in 1948. Then there was something else that was known, which was called Chargaff rules. Chargaff rules were named after a chemist named Erwin Chargaff. And Chargaff discovered, okay, let me just, for those who don't remember this, DNA is composed of sugars, it's composed of phosphates, and of 4 bases. The bases, for short, are called A, T, C, and G. What Chargaff discovered, that in any piece of DNA that he took, the number of A's was equal to the number of T's, the number of C's was equal to the number of G's. This also seems to indicate some sort of a two-kind structure, you know, this equals this equals that. Yet, when Pauling finally came out with a model for DNA, it was a crazy model. It had 3 strands in it. With 3 strands, how do you do complementarity with 3? It did not obey the Chargaff rules. It was built inside out. And in fact, it even couldn't hold together chemically. So here is with the model.
This is Linus Pauling's failed attempt to predict the structure of DNA. The problem with his triple helix model is that the phosphates form the helical core, with the bases pointing outwards. This would be impossible under normal cellular conditions. Each phosphate group is negatively charged, and so many negative charges forced together would repel each other, literally driving the structure apart.
So basically, he had the phosphates in the middle, but all the phosphates have a negative electric charge. And you know that similar electric charges repel each other. So this thing could not hold together. So what happened here? The greatest chemist of the world came up with a model which was built inside out, had the wrong number of strands, and disobeyed the basic rules of chemistry. So one of the things I've done in Brilliant Blunders was to try to get into the heads of the scientists that I discussed and to see why they made the mistakes they made. Now, this is not easy. Number one, I'm not a psychologist. Number two, even if I were, these people are dead. So I couldn't talk to Pauling himself, but I talked to all the people who were his grad students or postdocs at the time. I talked to all of them to try to find out, what was the thing here. So there were, in particular, I discussed this at some length in the book, but let me just give you a flavor of what I found out. There were, in particular, 3 questions that I wanted to answer. One is, why the rush? I told you that on the proteins, he took 13 years to publish his model. Do you know for how long he worked in earnest on the DNA model before he published this? 1 month. Why so fast? Second, he knew about the Chargaff rules. His model did not obey the Chargaff rules. A equals D, C equals G. Why did he forget that? And third, his molecule couldn't hold together chemically. What, the greatest chemist of the world doesn't remember the rules of chemistry? How is this possible? So let me give you my feel for the answers to these questions. Why the rush? Pauling was a genius, but he was still a human. He was afraid that somebody would publish it before him. He wasn't afraid of Watson and Crick. He barely knew of their existence. But he knew that both Maurice Wilkins in London and Lawrence Bragg in Cambridge had better X-ray diffraction images than his of DNA. And he was afraid that they would scoop it. So he published fast. Why did he forget the Chargaff rules? Here I have a theory, which makes him even more human. Pauling couldn't stand Erwin Chargaff. They were once on a boat trip together from the US to England. Pauling was a rather laid-back person. Chargaff was a very intense individual. Every time he would catch Pauling on the deck, he would bother him with his rules and things and so on. I think that Pauling basically took out of his head anything that has to do with Erwin Chargaff. What about the rules of chemistry? Pauling could not forget the rules of chemistry. He wrote the book on those, for heaven's sake. I think here he fell victim to his previous success. You see, what did he learn from the protein, from the alpha helix story? He learned that his original hunch was already correct. And all those 13 years of research only discovered that there were some details that need to be worked out. So he thought that he had the correct model, and that yes, it's the phosphates repel each other, but those are probably details that can be worked out. So he decided to gamble and he lost. The correct model was, of course, found by Watson and Crick. DNA is a double helix. The bases are inside. A connects with D, C connects with G, which automatically explains the Chargaff rules. And also, it obeys Pauling's idea of complementarity. You know half the molecule, you know the other half, immediately. What did Watson and Crick do once they discovered their model? Watson was in his 20s, Crick was in his 30s. They did what every young people would do in such a case. They went to the pub. This is the Eagle pub in Cambridge. And this is the place in Cambridge, they have a plaque now there, where Francis Crick stood in the middle of lunch and said, "We discovered the secret of life." The pub still exists in Cambridge. It's one of the known pubs. It's a wonderful pub. It also has there is a ceiling there where Royal Air Force pilots during World War II, when they were leaving for missions in Germany, they would write their names on that ceiling. That ceiling is still there. So, yes. I showed you Pauling when he was younger and when he was older. I now showed you Watson and Crick when they were younger. Here they are older. Francis Crick unfortunately passed. Jim Watson is still alive. I spoke to him several times while writing the book. He's still controversial as ever, and so on. I put this picture here. This is from a meeting on proteins that Pauling organized in the 50s for 3 reasons. Reason number 1, even though this is not a very large group of people, there are lots of Nobel laureates here. John Kendrew, Maurice Wilkins, Max Perutz, Linus Pauling, Lawrence Bragg, Jim Watson, Francis Crick, lots of Nobel laureates in such a small group. Number 2, there is only one woman, Beatrice Adolph from the Brooklyn Polytechnic. You go to a meeting of proteins today, it's 50-50. So some things have changed, thank goodness. Number 3, you see, this was a science meeting. This was not a business meeting. It wasn't a political meeting. Yet they all wear ties, for heaven's sake. I go to a meeting today, nobody wears a tie to a science meeting. So, some things have changed. The third person I want to talk about is Albert Einstein. This is the picture of Einstein which I like best, because when my hair gets a little bit longer, it looks just like that. And that's not the only resemblance. I like to say, you know, that Newton is dead, Einstein is dead, and I also don't feel so well. Now, Einstein did many things, of course, but his greatest achievement was general relativity. So I want to say something about that. So this is the main set of equations that describes general relativity. Now, some of you may be a little bit rusty on your general relativity. So I want to explain to you in just a couple of sentences the essence of general relativity. What general relativity tells us is the following. It tells us that gravity is not some mysterious force that acts across space. It tells us that what gravity does, it warps space-time in the same way that when I stand on a trampoline, I cause it to sag. Yes? Now, once I warp space like this, the objects find the shortest paths in that warped space. So, for example, the sun warps space in its vicinity, and the planets find the shortest paths in that warped space. Or a little bit like, you know, you throw a golf ball on the green, and it follows the undulations of the green, right? So that's the main idea. So gravity is not this mysterious thing, it is just a representation of the curvature of space because of massive bodies. Okay, now what does this equation tell us? For a moment here, ignore this term here. This thing here describes the geometry of space. Okay? This thing here describes the energy and mass content in any volume that you have. And this is the strength of gravity. So basically what this tells us is that mass and energy warp space, and that warping is what determines the strength of gravity. That's it. Okay? In other words, mass and energy tells space how to warp, and then warped space tells the mass how to move. That's it. Okay? Now, Einstein published this theory in 2015, and then in 2017, he tried to apply it to the whole universe. 2017 is now. He published it in 1915. We celebrated, 2 years ago, we celebrated 100 years to general relativity. And in 1917, he tried to apply it to the whole universe. Now, at that time, they didn't know about other galaxies at all in 1970. They only knew about stars in our own Milky Way galaxy. Now, Einstein thought that all the stars are fixed in their places because he wanted a universe that was in equilibrium. He thought that that is a more elegant solution, that the stars are fixed. But he understood immediately, look, how can they be fixed if because of gravity everything attracts everything else? Then this thing is going to collapse. It cannot stay fixed. So what he did was that at every point in space, if all the other masses were pulling something in this direction, he added an equal force in the other direction, a repulsive force that would keep it in equilibrium. And that's what this term does. In every point in space, a repulsive force exactly balances the other forces. Now, it turns out this was not a particularly good solution, but it was good enough for the time, and Einstein was very happy with it, that he managed to create a universe in equilibrium. But then what happened was that these two gentlemen, this Belgian priest and cosmologist, Georges Lemaitre and Edwin Hubble, discovered that our universe is actually expanding. It's not static, it's expanding. When Einstein heard that the universe is expanding, he said, wait a second, if it's expanding, I don't need that balancing force, because you see, if I throw this thing up, it's not in equilibrium at any given point. All that the gravity of the Earth does is it slows down the motion, and in this case it brings it even back. But it slows down the motion. So we say, if the universe is expanding, I don't need things to be in equilibrium. All that gravity will do is slow down the expansion. So he regretted having put that term in, and he took it out of his equations. Now, there is a whole industry that will tell you that he also called it the biggest blunder he ever made. I discussed this in the book, whether he actually said that or not. But in any case, he did regret having put that term in, and he took it out. But then guess what? In 1998, two groups of astronomers discovered that the expansion of our universe is not slowing down. It's speeding up. It's accelerating. It's as if I take this now and I throw this up, and not only it's not slowing down, it's accelerating towards the ceiling. You know, I once gave a talk about this specific topic, and there was a 7-year-old kid who was sitting in the front row, and I said, what would you think if you saw that this thing was accelerated to the ceiling? And the kid said, magic. So it would be like magic, you know, if it's accelerated. Now, do you know what's causing that acceleration? We're not sure yet, but as far as we can tell, the acceleration is caused by that term that Einstein took out of his equations. Some people are so smart that even when they do a mistake, it turns out to be a huge insight. Had Einstein not taken out that term from his equations, he could have predicted that the expansion of the universe should accelerate. This is what I wanted to tell you about the three scientists. But I now come back to the question of why I wrote a book about brilliant blunders in the first place. The main reason. And the main reason is the following. Usually when you hear descriptions of progress in science, and actually even not only in science, but in all creative enterprises, and by that I mean at school, even in universities, certainly in the media, when you hear descriptions of progress of science, it is usually described as a direct march to the truth from A to B. Now, those who work in science know that nothing can be further from the truth. Progress in science and in other creative enterprises is a zigzag path with many, many false starts, many blind alleys, and many points where you need to go back to the starting point. That's how progress is achieved. In other words, it involves blunders. Now, there are all kinds of blunders, and I don't want to give the wrong impression. There are blunders that people make because they are being sloppy. Those are inexcusable. There are blunders they make not because they are outright sloppy, but they are not thoughtful enough. They don't try to think about all possibilities. Those are also inexcusable. There are blunders that people make because they are very inexperienced. Those also should not happen because people should admit the fact that they are inexperienced and ask for guidance. So all of these blunders should not happen. Which blunders I'm advocating for? You see, we like to talk all the time about we want people to think what we call outside the box, in unconventional ways, with ideas outside the mainstream. Well, guess what? When you think outside the box, you may make a blunder. But if you don't do that, you may miss important breakthroughs. Those are the things I call brilliant blunders. Namely, when people try to think in new ways. Not all the time, by the way. There is a lot to be said for incremental progress in science, in small steps. That's how most science is progressing. But every now and then, you actually have to think a little bit differently. You see, this course is related to mathematics, so in mathematical terms, if you are stuck here at the middle of some potential, yes, if all you make is in infinitesimal motions, you will never get out. What you need is what is called a finite amplitude perturbation. That can take you out. We sometimes need that. Not all the time, because if you do that all the time, you're more likely to make mistakes most of the time. It's only every now and then. This is, by the way, the whole philosophy of startup companies. Startup companies, 4 years down the road, more than 50% of them fail. Yes? But every now and then, one of them is a huge success. And you cannot even predict which one will be a huge success. If somebody told me 20 years ago that the whole world is going to be communicating through a mechanism that allows you to write 140 characters, I would have said, this is crazy, what are you talking about? And now there is a president that communicates only that way. So, you never know which are going to be the great ideas, but you have to allow for the possibility to bring up those great ideas. So basically, let me finish here and just say that scientific blunders, and in fact, in every creative enterprise, but of the type that I call brilliant blunders, can actually be the portals to discovery. Thank you very much. I'll be happy to answer some questions if there are. Maybe you can turn on lights. You want to turn, Jose, you want to turn on all the lights? And if there are some questions, I'll be ready to answer.
Yes, I have a question.
Yes. Yes.
In English or in Spanish?
What?
I ask you in English.
You
or in
ask me
Spanish?
in English if you can. If you cannot, ask in Spanish. Jose or Roberto will
No,
answer.
because of other people. Well, doesn't matter. I don't understand. Well, it's a naive question.
Please.
Bueno, I don't understand why in the general relativity theory of Einstein, I understand that the gravity makes
Space.
ondulation, the space and
Curve.
time, yes. But I don't understand in the opposite side why time and space make the all the planets and the stars the movement, and why the movement is circular. Why?
Okay, so, okay, I don't know if you heard the question. She wants to understand.
Shall I translate?
No, no, if people sit here, it means that they understand what I'm saying.
I don't know.
I hope. Or they wouldn't sit here.